Welcome to the Getting Started with GeoStudio video series. This tutorial introduces how to use the AirW product of GeoStudio 2012. This tutorial video has been designed to help walk new users through the basics of setting up a simple airflow analysis in AirW. So, if you are new to AirW and are not sure where to start, you have come to the right place. The main topics that will be covered in the tutorial will be how to create an analysis in AirW by using the Define view to set up the analysis, the Solve Manager to solve the numerical analysis, and the options available in Results view to gain a deeper understanding of the analysis. If you are not familiar with GeoStudio products, it is recommended that you start with the tutorial videos for SeepW, Sigma W, or Slope W to gain an understanding of the tools available for drawing your geometry domain, creating sketches, or explanations on basic options that are available in all GeoStudio products. This tutorial video will mainly discuss AirW options and tools where they differ from SeepW, Sigma W, or Slope W. Note, AirW is used in conjunction with SeepW or TempW to model the flow regime prior to modeling the airflow problem. So, let's get started. This example will include two analyses. The first will be a steady-state water transfer analysis using SeepW to determine how much water will flow into a tunnel that is located below the regional water table. The second analysis will illustrate how much water will flow into the same tunnel if the air in the tunnel is pressurized to 50 kilopascals. We will start with a steady-state water transfer analysis already created, with our ground region and tunnel already drawn. If you are unsure of how to use the visualization sketching tools or draw the geometry regions, please refer to the Sketching Tools and Geometry video tutorial or the Introduction tutorial videos to SeepW, Sigma W, or Slope W. Now we will add the material to our analysis. I will go to Key in Materials to open the Materials Define window. I will add a new material and give my material a name. I will then choose the Saturated/Unsaturated option from the drop-down menu. Here, I can create a hydraulic conductivity and volumetric water content function for my material. More information on the hydraulic model options can be viewed in the SeepW Estimating Hydraulic Functions tutorial video. We will first add the volumetric water content function by clicking on the ellipsis button. We will simply add a volumetric water content function for a silty clay sample material with a saturated water content or porosity of 0.47. I will also include a coefficient of volume compressibility value of 1e⁻⁴. Next, I will add a hydraulic conductivity function by clicking on the appropriate ellipsis button. I will add a function using the silty clay volumetric water content function and a saturated hydraulic conductivity of 0.01 meters per day and a residual water content of 0.05. Now we will add the material to our domain by choosing Draw Materials. We will simply choose the silty clay material and assign it to our soil region. We will not apply any material properties to the tunnel as it is considered to be an open circular region. Boundary conditions can be created and assigned in a similar way as the materials. I will choose Key in Boundary Conditions to open the Define Boundary Conditions window. The potential seepage phase and zero pressure boundary conditions are created by default. I will also add a new hydraulic boundary condition to represent the regional water table height at the far field boundaries. I will use the total head boundary condition with a constant value of 16 meters. Now I can add the boundary conditions to my domain to represent the water table on the far field boundaries and the seepage face along the surface of the tunnel. Now we are ready to add our coupled airflow analysis to the analysis tree. We will go into the Key in Analyses window and clone the current water transfer analysis. We will simply change the name of our analysis and activate airflow on our domain. The geometry of the domain is considered project-specific, but the material properties, boundary conditions, and analysis type can be modified to simulate different scenarios of the analysis. Now we must return to our Define window and set up the airflow properties for our analyses. We will go into the Key in Materials Define window and clone the current material. This material will include the same volumetric water content and hydraulic conductivity functions as the water transfer only analysis. But we will now add an air conductivity function to help define the air flow within the domain. We will click on the appropriate ellipsis button and estimate the air function. We will use the silty clay volumetric water content function and an air conductivity of 1 meter per day. Now we can add this material to the domain for the tunneling with airflow analysis. Now we are ready to define our boundary conditions. We will go to Key in Boundary Conditions. The default boundary condition of a 0 atmospheric pressure is already added to the boundary conditions list. We will add a constant pressure boundary condition to simulate the pressurized air within the tunnel and change the value to 50 kilopascals. We will add the 0 atmospheric pressure boundary condition to the surface of the soil domain and the tunnel pressure to the line representing the outer rim of the tunnel. If at any time you wish to only see the airflow boundary conditions on the domain and remove the hydraulic boundary conditions from the visualization, you can change the drop-down menu from All to Air. Note, the hydraulic boundary conditions are still applied to the domain, but are simply not a part of the visualization. Our next step will be to look at the default mesh. We can see that a default global element size is set to 1 meter. We will refine the mesh by changing this value to 1.25 meters. We will also click on the perimeter line of the tunnel and change the element size to be half of the default element length. More information on the meshing options can be found in the engineering books or the Mesh Options and Constraints tutorial video. Now we can solve all of our analyses by clicking on the Start button in the Solve Manager. Once solved, the window will automatically change to the Results view instead of the Define view. By default, the total head contours will appear along with the phreatic surface as a blue dashed line. You can change the contours that are being shown on the domain in the Results window by choosing a different contour type in the drop-down menu. You can also add new contour options by clicking on the Draw Contours button. You can change the shading methods used to draw your contours, add a legend, or change the increments and starting and ending values of your contours. Other items can be added by clicking on the Add button and choosing the type of results contour you would like to create. We will go to our second analysis to view the pore-water pressure contours when the air pressure is added to the tunnel. We will go back into the Draw Contours window and add a new contour item. Here, we will add the matrix suction contours to the list for the airflow analysis. Currently, we can only see the water velocity vectors on the domain. We can go to Draw Velocity Vectors to add the air velocity vectors to the domain as well. You can also add labels to your contours using the Draw Contour Labels button and clicking on the contour lines where you want labels to be painted. You can choose what items are activated in the results window at any time using the View Preferences toolbar along the right side of the screen. Here you can toggle on and off results information such as the velocity vectors, contours, or you can view your mesh, boundary conditions, material properties, or toggle on and off geometry items such as the regions or point numbers. Next, we will create a graph to help us gain a better understanding of our analysis. By default, for all SEEP-W analyses, the conductivity versus matrix suction graph shows that the resulting conductivity matches the hydraulic conductivity function that was entered in the Key in Materials Define window. This is one of the checks on convergence. More information on convergence graphs can be found in the engineering books or the SEEP-W Convergence and Under Relaxation tutorial video. We will add a graph that shows the total rate of discharge of water through the walls of the tunnel. We will choose our node locations to be along the perimeter of the tunnel line. We will choose water flow, water flux versus time, and toggle on the sum y versus average x option. Now we can see that the total discharge through the tunnel when there is air pressure is equal to approximately 0.076 cubic meters per day. Note, the negative sign here indicates that water is leaving the domain. When we change to the first analysis where air pressure was not added to the tunnel, we can see that the discharge increases to 0.144 cubic meters per day. More information on the other options available in the results view can be viewed in the SEEP-W, Sigma-W, or Slope-W tutorial videos. We have now reached the end of this introductory tutorial. Note that not all of the powerful features of AirW 2012 have been used or discussed here. Further information on each command can be found in the online help, supporting documentation for AirW, as well as in other tutorial videos of the Getting Started with GeoStudio video series. Thank you for watching.